So I'm going to talk about Koopman operator methods for analysis of tropical climate variability. So hopefully the next two slides aren't too boring if you were paying attention to Dimitri's talk, but we'll all start on the same page. So we're going to consider some continuous time today dynamical system. We'll have some set of states, x of t, a flow map, so just moving our states forward in time, and importantly, observables, so functions g of the state. And we're going to think about dynamical systems today through these observables. And I'm going to argue this is kind of a natural way to think about the climate system anyway. We never have access to the state of the Earth at any given time. It's some very, very, very high-dimensional system. We do have access to things we observe, these functions. So for example, the observables could be zonal wind at the coordinate of your choice, or some average SST. And so if we think about our dynamics here as observables, we can then induce a linear operator on this infinite space of functions that we call the Koopman operator. So this is linear. We're denoted UT, and it will describe evolution through action on these observables. So UT applied to a function g, evaluated at some time s, is going to equal g of x of s plus t, where we've pushed forward that flow map inside the function. And so this problem is very nice in that we've taken problems about nonlinear dynamics to equivalent linear ones. But the trade that we're making is we're moving from finite dimensional space to infinite dimensional problems. For a wide class of systems, namely those with an ergodic invariant probability measure, we can introduce an additional operator, a skew adjoint operator v that we call the Koopman generator. And it generates the Koopman operator in that ETV is equal to UT. And we can think of V as some sort of generalized derivative with a form that we can get there. One reason this is a particularly nice form to have is then spectral decomposition acts as coherent feature extraction, where coherent features are these eigenfunctions zeta k that evolve with a known frequency in a known way with its eigenvalue or eigenfrequency omega k. And because of this nice form, these can be pretty useful for analysis and modeling of dynamical systems, especially for low-order models. And there's been a lot of previous work here to think about approximations of these from data. And this includes work by Gary and Dimitri's. So how this talk will go is in the first part, I'm going to introduce a little bit more theory, if only to motivate why we should choose algorithms that are spectrally consistent rather than maybe the simplest thing to implement. And then I will talk about Koopman methods in practice, in applications to true tropical oscillations, the QBO and the MJO. So the first question to ask is, why care about the spectral consistency notion? Why care about spectral accuracy? And for those familiar with dynamic mode decomposition, the question you might be asking is, why can't we just always use DMD? And so I've chosen a very nice example. It is in discrete time, but it works quite nicely. I've actually taken this from Matt Colebrook. But we're going to consider right shifts on infinite two-sided sequences. So a right shift is we just take something at one entry and move it one to the right. And if we could write down some sort of infinite matrix to represent this operation, it might look something like this, right? Zeros on the diagonal, ones on the upper diagonal. I think this is a pretty reasonable way to think about the system. And it has several special properties, the most important of which might be it has unitary evolution. All of its spectrum is going to be the unit circle. Notably, due to this kind of infinite dimensional operator, it does have continuous spectra. It has no true eigenfunctions in this space, or sorry, eigenvectors. But it does have spectral properties that are pretty easy to understand. And so we have this infinite dimensional matrix. We can then say, well, we could probably write this down a nice finite dimensional approximation. That'll look something like this, the same thing, but we've just truncated it to be finite, but this has very different spectral properties. The spectrum is 0. This is going to have nilpotent evolution. But this is the best least squares approximation. And so it is the DMD approximation if you use such an algorithm. But it's not necessarily going to give you the spectral properties that you want. And so if you're interested in this coherent feature extraction problem, where we're doing identification, or maybe in prediction by frequency, this is probably not going to be the best answer.
So how do you do the continuous? Is it just the continuous spectra is just that any eigenvalue you have, you add a little bit to it, and that's also an eigenvalue or something like that?
So we'll talk a little bit about it, but maybe to summarize very briefly is like matrices, you can write down like AV equals some lambda v omega k, right? So instead of that, in infinite dimensional space, you'll have operator A, F will be like this. But we'll have some integral. This is some projection valued measure. And in nice systems, you can split this. Like this could be partially like atomic, like a probability measure. But it could also just be some kind of gross integral measure that had this continuity. So sometimes it looks a bit like this, not always. That's what I mean by that. And I'll give you an example in like 2 slides of where it's kind of all this. Yeah. But for this one example, just so I don't get accused of cheating, it's pretty easy to fix. You can pop a 1 on the bottom left diagonal, make it from a right shift to a circular shift, and then we get our spectral properties back. Eigenvalues are the roots of unity, unitary evolution. But again, it's not the best least squares approximation. And that's not necessarily what we'll be showing today, but the choice might be important depending on your application. So the first issue with going from finite dimensional linear operators to infinite dimensional linear operators, specifically the Koopman operator, is that the spectrum isn't often discrete. It's often not discrete, even if it has all of these like nice point values that come with a sum. So recall that our Koopman generator looks like some sort of generalized derivative. It actually is a generalized derivative called a derivation. And so it's going to have a chain rule. And so what that means is if we have 2 eigenpairs, alpha and A, and beta and B, V applied to A times B is going to be alpha plus beta times A times B. So now we've generated a new eigenvalue, alpha plus beta, from our chain rule. And we can do this for every single integer linear combination of eigenvalues. So if we have one non-trivial eigenvalue, operator is unbounded. More annoyingly, perhaps, is if we have irrational multiples as eigenvalues, our eigenvalues are going to be dense in the imaginary line. They're going to be arbitrarily close together. And so this will pose some issues for computational stability unless you do some sort of preconditioning to deal with this. The second thing, and what I alluded to for Noah's question, is that infinite dimensional operators can also have continuous spectra. So if we have a true eigenvalue eigenfunction pair for our system, this is going to correspond to periodic, or maybe in the case of an infinite sum, quasi-periodic dynamics. But we know that doesn't always exist, right? Like we have systems like Lorentz that are characterized by a decay of correlations, but this formalism for the Koopman generator doesn't necessarily exist. And so it's kind of in places like these where we have this decay of correlations, we're going to have a spectrum that looks more like this rather than something with a sum. In fact, Lorentz 63 only has continuous spectra besides the trivial constant eigenfunction and the 0 eigenvalue. So a good approximation algorithm should at least nominally try to take in both that we have point eigenvalues and continuous eigenvalues. And so I'm going to kind of sketch out a strategy to deal with this. First, you'll approximate V, our generator, with some trajectory data. We'll often do this on a kernel basis. It gives you some nice RKHS formalism if you're familiar with that. We'll then apply some sort of bounded transformation to V. I mentioned that this might not necessarily be bounded. In fact, it usually isn't. So I'll work with a bounded version of this that we can then get back through some eigenvalue problems. We'll then do a smoothing step, and then we'll do some eigenvalue problem. And so I'm going to note again that these 2 steps in the middle, where we look at something bounded and then we smooth it, force the operator that we're working with to be compact. So this is going to mean it has well-behaved spectra. namely that we're going to, at the very least, have spectrum that is separated from each other. So we're not going to have any numerical issues with trying to approximate numbers that are arbitrarily close together. This strategy is also going to give us a nice convergence result called strong dynamical convergence. And this gives us Koopman operator convergence and spectral consistency. And slightly more formally, these algorithms are going to find an approximate generator v tau that converges to the true operator as we take tau to 0 in this strong dynamical sense. I will summarize, if a bit qualitatively, what properties this gives us. So it's going to give us that the Koopman operator converges for all times t. So where t is 10, t is 100, all of these will work. We're going to have spectral inclusion. So to say, we're going to be able to achieve all of our eigenvalues. For every lambda in the spectrum of our original operator, we can write down a sequence of lambdas from our approximate operator that converge. And finally, we're going to get convergence of the projection valued measure. You can think of this as a sense of convergence for the continuous spectra. It really means that this measure right here converges nicely on suitable sets where that is possible. So these have some nice convergence results. They also have pretty good numerical stability generally. And the results look pretty nice when we're thinking about trying to target slowly decorrelating observables, coherent features with known eigenfrequencies. So this is a less exciting version of the plot that Dimitris showed yesterday, where I have input data from a Lorentz 63 trajectory and put it through one of these algorithms. And I'm showing two eigenfunction eigenvalue pairs that come from this. So on the left, I printed on the top, has a frequency of about 7.5. On the right, it has a frequency of about 4.8. And you'll see that even though we know that there are going to be no true Koopman eigenfunctions, we get something that looks fairly good, like what we would expect it to. This top row is the real part of the eigenfunction. So something that is perfect should just be a complex sinusoid. So the real part looks approximately like a complex sinusoid, evolving with our frequency. We can then also kind of trace this eigenfunction in the complex plane, where perfection would be tracing out the unit circle. And we're doing pretty well here as well. And this third thing on the bottom is essentially as if we've taken our eigenfunctions and projected our data upon it. So we're kind of seeing our Koopman eigenmode on the attractor. And you can kind of...
Sorry. So how did you pick these particular spectral values?
I've picked them through the Dirichlet energy that comes with them. So through a measure of... So you can put in all of these. They have some sorting metric. This is 2 and 30. I'm sorting them by the amount, like an approximate version of their like variability. Yeah, like a Sobolev norm.
And do they correspond to peaks in the spectral measure?
That is what we certainly hope. That is kind of what the theoretical results say. I mean, you can't ever really know, I think, given that like there are results that you need at least two parameters to converge to such a thing. It's not something we can know maybe quantitatively. I will note that this eigenfunction on the left is very similar to one that everybody finds. I think one of your methods finds it. The methods of Matt find something very similar. So
I was just curious if there's a correlation, if you observe a correlation between peaks in the spectral measure and regular eigenfunctions. I mean, you're finding low Dirichlet energy in your language, I guess.
I would hope so, but I don't know.
You haven't observed any correlation like that?
I haven't observed any correlation because I don't think I would know how to measure these peaks. But hopefully, yes, is the answer. But maybe to kind of summarize what we're trying to get here is that we're able to identify these slowly decorrelating observables even in chaotic systems, right? Like for Lorentz, the Lyapunov time with these parameter combinations is about 1.2. We're getting good correlation long past that Lyapunov time. So these are at least these algorithms are able to identify slowly decorrelating observables, and notably a frequency at which they evolve. And so these are going to work in a lot of settings, with even those with continuous spectra, and they have fairly numerically stable behavior to like data perturbations, maybe more so than traditional DMD methods without. So the smoothing adds some nice preconditioning. Okay. So now I'll talk about using these in practice. And so we're going to look at two different oscillations. We're going to look at interactions between the QBO and the annual cycle. And then we're going to use it to define a smoother, more predictable index for the MJO. And I'm going to kind of go through this in a more pedagogical style in some sense, in that kind of give you an idea of how we can actually like use these from data and kind of identify what are the right things. So the first thing I will talk about is the quasi-biennial oscillation, or the QBO. So this is a 28-month oscillation in the equatorial stratosphere. So this is this plot on the left, where we have time on the x-axis and like pressure or height on the y-axis. And so if you look at this, you can see these very clear descending easterly and westerly jets with this 28-month period. These are extremely regular. However, there is kind of some meandering as it descends, which might be due to the annual cycle. The QBO is known to affect weather and climate. There is an intensification of the polar vortex associated with one of the phases. We think this might interact with MJO predictability. But probably the reason that many people in this room are familiar with this is that we use the QBO, or our lack of constraints upon the QBO are due to our gravity wave parameterizations in GCMs. So if you put these in a, I think, 4 times CO2 GCM experiment and compare all of the models together, about a third of the models slow down the period by about 8 months. About a third of the models increase the period by about, decrease the period by about 8 months. And a third of the models, this completely disappears. And so this is likely due to uncertainty in gravity wave parameterizations. But our full understanding isn't really here. And we might want to improve that for that cause. So as I noted with this kind of meandering of the QBO descent, is that the QBO is known to be affected by the annual cycle. And this leads to kind of these variations in the descent rate in the QBO period. It's usually called phase locking, and it's most easily seen by this histogram right here, where I'm going to ask when there is a QBO zero crossing at a particular height. So what I'm asking is, when do we go from easterly QBO to westerly QBO, or westerly QBO to easterly QBO as we descend? And I've put a histogram of asking when that is and the month on the x-axis. And this is a pretty strong bimodal distribution. We have a bunch of transitions in April and May, and almost no transitions in July and August. And exactly the cause of this is not fully known. And we're going to use these methods to try to separate the QBO from the annual cycle, quantitatively like measure this effect, and then you can use that to investigate the causes of this slowing down. So we're just going to input 40 years of era 5 zonally average zonal winds, and at 7 pressure levels in the lower stratosphere. So data will look something like this. We are actually giving it pole to pole, not just the equator, but this is so regular that it doesn't really end up mattering. And we're going to get an output where we have our Koopman eigenfunctions. I've just plotted the real and imaginary part over time, and some eigenfrequency. I've selected this particular one here because the eigenfrequency of 0.427 times a year exactly corresponds to a period of 28 months, which is this QBO. So we can say we have some eigenfunction that oscillates with a frequency of something that we're interested in, and we can then hope that our Koopman mode is associated with this phenomena. And it is. If we kind of project our data and make our Koopman mode to go with this, we get something that has the attributes of the QBO that we're looking for, a 28-month period, descending easterly and westerly jets. Notably, this descent is extremely regular, much more regular than in the atmosphere. And so we can we'll be able to investigate that further. And we'll do this by looking at all of the eigenfrequencies, or at least a good number of them, instead of just the one that we were looking at before with this 0.427 times per year. So plotted is the eigenfrequencies that come out of this analysis. This y-axis is our frequency part, and I plotted, and that's in units of times per year. So I'll talk about this more in a second, but on 1, 2, 3, and 4, this is things lie here, should be once a year, twice a year, 3 times a year, 4 times a year, where I have these solid lines. This real part is this Dirichlet energy, so you should think of things that have very small absolute value of real part, are more regular, we have some more confidence in them. Things way over there are something that we don't really want to look at. And I've colored all of our scatter points by the variance of the Koopman mode. So something darker has more variance from our data, something lighter, hopefully we can ignore. But I'm going to sort all of these eigenfrequencies, or all of our modes based on their eigenfrequencies. And we can use that to do a pretty good job of kind of pulling apart a reanalysis. So here's some reanalysis for comparison. I'll first say I want to look at everything that is associated with the seasonal cycle. So this is going to be things, again, with a period of a frequency of once a year, twice a year, 3 times a year, this harmonics. I will add all of their modes together and then get an annual cycle composite mode that looks like this. And this looks pretty good. We have our semi-annual oscillation in the upper stratosphere, none of our QBO. We can then do the same thing, thinking about our quasi-biennial oscillation. So take things that have frequencies that correspond to a period of once every 28 months, or one of its harmonics, and add them together. We get a bit more structure than in the previous single frequency that I showed you before, but still none of this meandering behavior. But we can get the meandering behavior. We're going to get this through what I'm going to call these interaction modes, where you have frequencies that are 1 plus our frequency of the QBO, 1 minus. You can take all of these together and get a plot that looks like this. It's not super interpretable on its own, but you can add it to that plot C above it and get something that I call the QBO with annual cycle interactions. And so I'm going to call this, again, the QBO that we observe. It has the frequency that we're looking for. It kind of has these meandering jets. And we're going to be able to kind of use this separation between nonlinear interactions and the QBO to investigate this kind of phase locking behavior. I also want to note that if we also add in the annual cycle mode, we get most of the reanalysis in some sense, where we have isolated all of these kind of low frequency behaviors and large scale behavior that we're interested in. We've gotten rid of a lot of the high frequency variability that isn't so useful for this problem. So this is nice that at least in this kind of constrained space, we know what all of our modes are doing and we kind of interpret them fairly simply. We can then first say, okay, how does this plot necessarily change if we're looking between the QBO we observe with annual cycle interactions and our pure QBO? And so I'm going to make this same histogram, but for our kind of isolated QBO that I got from the data. And this is a lot closer to uniform than this plot on the left. There's really very little, if any, influence of the seasonal cycle on like when we go from a descending westerly to descending easterly jet. Obviously, this isn't perfectly uniform, but we only have 40 years of data, so we're going between 1 and 4. There's not really much you can do there. But we're going to kind of use the differences of what we've isolated and what is actually going on to quantify the effect of the annual cycle and test causes of the phase locking. And there are several hypothesized causes for the phase locking of the QBO. We'll only look at one of them today, which is variations in upwelling. But this could also be seeding from the SIO or some variations in wave forcing that come with just the gravity wave forcings that drive the QBO.
Can I ask you, so I mean, I kind of get you add more modes, eventually you'll converge to the way the data looked.
Mm-hmm.
So I kind of get the story, like, that you're trying to, like, you're approximating a continuous spectrum, and then you add more modes, you get closer to that. It starts to look more like real data. But how much of it comes from the kind of eigenvalue to space reconstruction process that you're using? Like, because there's a fair amount of noise just in that kind of downscaling problem, if you will.
Yeah, there's definitely noise in the downscaling, and then so the harmonics are both in that, yeah, you can't express everything as like a simple eigenfunction, but it also comes from that chain rule property of this thing being a derivation of like, I'll just, like a mode at 1, 2, 3, and 4 has to exist in this like initial operator if we have the mode 1. So yeah, I think it's both. And yeah, I think as you said, like a perfect sine wave is not going to get kind of this dimensionality.
But have you disentangled the two, like one being this eigenvalue summing spectrum stuff, and then the other being like given eigenvalues, all of them, or some truncation going to space map?
No, but I think part of the reason is these like eigenfunctions that we're getting are eigenfunctions of our approximate operator, so they don't have a perfect sine wave form as it is. I think if you assumed everything had perfect sine waves, you could find that most of it's actually like the eigenfunction property. It's just that like you can't, like you need infinite sine waves to approximate a square wave. Yeah, so my answer is no, but it's definitely both. So we can try to figure out exactly what quantitatively is happening here. And so we're going to do that with these modes, and we're going to do it by looking at how the seasonal cycle affects the QBO descent rate. We're going to do this by looking at something very specific, maybe a bit simple, but it does work here. Is we're going to look at the descent of our zero crossing line, and that's how we're going to define like how fast the QBO moves. And so I've plotted that on the upper left here from our pure QBO mode, where on the x-axis we have time, so over the year. And on the y-axis we have this descent rate in meters per day. So something very low will be a very fast descent, something high will be a slow descent. And what you'll notice in our pure QBO, or I hope that you agree, is that there's really very little variation that seems to be due at all to the annual cycle here. We have kind of isolated it from the annual cycle. And we can then compare this to the QBO with our annual cycle interactions, where we have a pretty distinct bimodal trend in QBO speeds. We're at the beginning of the year, and in August and September, we have a very, very slow QBO. And in April and May, and October and November, we have something that's pretty fast. And we can quantitatively say that the annual cycle impact on QBO descent rates is just going to be the difference of these two plots. And so we kind of just invert this bimodal distribution, but it's still pretty distinct. There are times of the year when on average the QBO is much faster, times through the year where on average the QBO is much slower. And so although this is like kind of a simple operation, we're just subtracting plots, we haven't been able to do this before. Like getting this pure QBO, I think, is something that people have really struggled with. So you can't really study this problem, or the problem hadn't really been studied comprehensively with data previously. And so I'll take a second to show kind of the one set of results here. We can relate this to variations in upwelling. So this is kind of a big plot, but I'm going to ask how changes in the upwelling in the equator is going to relate to this change in descent rate. And so I'm tracking descent rate, which kind of goes down the column as time goes on. So we have to look at upwelling at several layers, which is this kind of y-axis where are we measuring the upwelling. And on the left, we're just going to ask how the variation of upwelling affects the descent rate with a linear regression. So on this left, we have a slope, And so a slope of about -1 will be, we have an increase in 1 meter per day of upwelling. We're going to have a decrease of 1 meter per day in this QBO speed. And this is kind of, goes with a very kind of naive but not incorrect assumption that if we have something descending, we have an equal increase in wind going up, this will slow down. And at about 30 HPA and around there, we do get the slope of 1. Like this kind of naive picture actually works pretty well. And on the right, I'm showing the R² value for all of these linear regressions, where by the time we get to kind of the upper stratosphere, about 15 HPA, upwelling explains nearly 80% of the variability in this descent rate. So this is a pretty significant portion of how this phase locking behavior appears. And we did some later experiments comparing the other things, some other causes, but to first order, this upwelling really seems to be what is affecting this QBO descent. We have a fun little back of the envelope climate estimate that we assume linear regressions are flawless and nothing else changes, that in 4 times CO2 experiments, the upwelling increases by about 9 meters per day. So that's approximately a 30% reduction in QBO speed, again, assuming nothing else changes. But this is an increased period to about 40 months from the original 28. So yeah, it does indicate that these large changes in the QBO aren't necessarily, period, from the GCMs aren't necessarily crazy, although it doesn't really give much evidence beyond that for one thing or another. So the second problem I'm going to talk about is the MJO. So kind of simply, the MJO is some stormy and wet area with some sunny and dry area that propagates eastward in the tropics. It has an oscillation period from between 30 and 60 days. So if you look at how it propagates on the globe, it looks something like this, where I believe what they're plotting here is velocity potential. We can kind of see these large areas of increased and decreased precipitation as they propagate eastward. So this is known to influence a huge amount of global climate, tropical cyclones, monsoons, extremes. Notably, the MJO has received a lot of focus in that people think it might be the key to this kind of seasonal to subseasonal weather prediction, as it is a large source of predictivity, and it has kind of this intraseasonal period. And so we're going to ask if we can use these Koopman methods to define kind of a nice index for the MJO that we might want to use in these problems. So I'm going to kind of show what we're working with, and I'm going to show the variables that we're going to use to detect the MJO in a particular year. This is the year of the tropical convection campaign. I've chosen this because it's fairly well studied, and it has kind of fairly well defined in the literature MJO events. So in this plot, I have outgoing long-wave radiation, which is some proxy for convection. You have longitude on the x-axis, time on the east axis, so that eastward propagation will go this way. And so there are 2 fairly well-defined MJO events here. You can see this first one originates here, mid-October, kind of propagates with the following dry, and one right here, although this kind of has some convection that stays paused. And also note that this is bandpass data. It's kind of noisy, but these are what has been kind of defined as the MJOs during this time. We'll also usually look at zonal wind at 2 periods. So I have it, at 2 pressure levels. So I'm plotting it here at 850 HPA, but we'll also look at input wind of 200 HPA. And then again, I'll just kind of highlight these 2 MJOs that are kind of defined in the data. And they kind of have this approximately 5 meters per second propagation. But this is what we're going to look for here. We're going to hope that from data we can pull something out with these Koopman variables, this Koopman decomposition. And so we're going to input some, we're going to normalize these so they have equal standard deviation, but we're not going to do any bandpassing besides the time filtering that comes from Koopman itself at several levels. And unlike in our previous plot, which everything was very, very nice, we're going to determine relevant modes based on period, variance, and some sort of autocorrelation decay, which you can kind of think of as a metric for how predictable a given mode is. And so this is a very similar plot to what I showed before. I've changed units somewhat for the QBO. Is now for the MJO, I'm putting period on the y-axis. So we're going to be focusing on things in this intraseasonal band from 30 to 90 days, which I blocked off. And on the x-axis, I'm going to have something that I'm going to call my maximal autocorrelation error. So like how bad are we doing as compared to a perfect Koopman eigenfunction. So something that is perfect will have no autocorrelation error. We'll maintain it at our frequency as far as we like. This metric stops at 1. That's the worst you can do. And what I have found is that there are going to be 2 modes that we can highlight in the frequency band we're interested in that have some predictability according to this metric, at the very least. So this first one that is on the left, I'm going to call our MJO mode, and we'll be able to see that better in a moment. This other mode we won't talk about today, but after analysis, we're going to call it a possible BSISO mode, which is the boreal summer intraseasonal oscillation. And this is associated with like the monsoon. It's a meridional mode that's active in the summer. But we won't talk about it today. But it's pretty clear to be that way.
Say quickly what the autocorrelation error is.
So I chose it for, so basically you're asking, what is your error between, this is going to be some true, if this was perfect, it's going to look something like this, and your mode. So if these are perfect, this would be 1. OK, that's what it is technically. So it's asking like how close does it behave to something that looks like this over a certain time period. So I'm saying maximize this over 45 days.
It's like a pseudo-spectrum.
Yeah.
It's like the epsilon you put in for a pseudo-spectrum.
Yeah, you could also think about it.
Oh.
Yeah, you could also think about it as you can relate it to the metric of, the pseudo-spectrum is you can say that if this is 0, it's going to be a true eigenvalue, and if it's very small, it's going to come in the epsilon spectrum.
So this plot to the left is good.
To the left is good. To the right is bad. Well, it maxes. I've designed it so that 1 is the worst value it can be. And this isolates these 2 nicely. I also did this with the other metric that I used previously. And you get kind of this third mode here, which seems.
So you did Dirichlet energy.
Yeah, this mode traverses kind of over here. This seems to be some weird sort of trend intraseasonal mode, but it didn't clearly map onto anything we knew about. And was kind of hoping to say we're looking for things with kind of coherent propagation. But we did analyze this, and it is kind of nothing. But yes. So the question is, does this Koopman mode that we isolated effectively, again, isolate the MJO? And we're doing, I think, a fairly good job. So this is the same variable field before, same time span, but I have added these contours in black to indicate the MJO mode. And so you can see that it definitely has like power in some other places. And actually, this appears to be kind of the back of this mode, where it kind of starts over here and propagates on. But we are fairly well identifying MJO activity here, and kind of less so at the very top, where there was, of course, convective activity that did some propagation, but it wasn't determined to be a pure MJO. And we can do the same thing looking at zonal wind. And again, same field, but we have just, on top of this, put our Koopman mode. And we are fairly well, at least, identifying these modes of propagating convection and isolating the MJO.
Are your modes 2D or they're 1D and you're propagating the mode in these pictures? The color is the mode, right?
Oh, sorry. The color is the variable field from like 2 slides ago. These dotted lines are the Koopman mode that I've like projected on the index.
Okay, which is 2D.
It is 2D, yeah.
So this is just the Koopman mode of, well, okay, but I mean, normally you have them at a particular time, but you're saying it's base time.
I've taken like our eigenfunction, like our index, and projected the data onto it. So it is, oh, so these are 2D in this plot in that they're like spatio-temporal.
Yeah.
Yes.
So the mode itself is spatio-temporal, or are you vecting the, like how do you get the time in the picture here from the mode?
So you have your kind of eigenfunction, and then you can then project your data onto this in the same way that you might for like EOFs.
So it's like you've made a movie of
Yes, I've made a movie of modes.
1D, in this picture, 1D modes.
Yes.
Okay. And then these are level set contours or something, the black and the...
Yeah, they're level set contours. The dotted lines are negative, the solid lines are positive. They don't have the same magnitude, and I think that's fine. You have harmonics of this. Obviously, not the only thing like happening in zonal wind here is the MJO. There's like really a lot of variability in these fields, especially in this area. But yes, dotted lines are negative, the positive lines are positive, and they're same units. And then just kind of as an index, like we have these spatial temporal modes, but I can just say that I'm looking for an index. I just want that Koopman eigenfunction, which I'm tracing in the complex plane. This traces counterclockwise, and I've kind of did 2 colors here. So this red just indicates the period from mid-October to kind of mid-February where this ends. And what you can see here, which I think is kind of nice, especially when I can compare this to the conventional index, is you get 2 loops that go with our 2 MJO periods. Something that starts here, that goes around, something much larger to go for the more intense second MJO. And so this as an index is at least interpretable in that form. So how is this done usually? The MJO is often defined by this object we call the RMM, or the real-time multivariate MJO index. And so all the RMM is that you will take the first 2 principal components of the same wind fields, but these wind fields will be normalized. We also normalize them. There's some deseasonalization, and then the interannual variability will be removed in some way, usually by subtracting off some means. And over the period that I showed, this is what our index looks like, which I would argue is not very predictable, not very easy to look at. Our Koopman mode is better in this way. It propagates much more smoothly. It's kind of more predictable, generally. I will say that like the RMM is very useful for analysis. A lot of work has been done here. And I'll kind of show these vaguely at least look at the same picture of the MJO. But if we're looking at something, and I'll just highlight these same times in red, this is much easier to understand and much easier to predict, and it has kind of this coherent propagation that we're looking for. So again, I've provided something that's much smoother. I would say these plots look very different. And I do want to say we haven't completely thrown out what we think of the MJO. If we compare the RMM with the Koopman mode, so this traditional RMM mode will be in blue, our Koopman mode will be in red, and I put the analogous kind of indices in each part, the real imaginary part. These co-vary fairly well. I think they have about a 60% or a 0.6 correlation coefficient. And if we look at the composite phases where we're saying if we divide our MJO up into 8 phases, do these phases approximately match in our variable fields? They do. We have convection at the same times in approximately the same places, and they propagate at relatively nice speeds. But all we should really get out of that plot here is that we have Koopman phases as defined on the right or the left, the RMM phase on the right, and that they aren't that different to area and where we want to be. So maybe I'm a little scared of showing this slide. This is very fresh work, but these provide a more predictable index. And I'm not saying that we should do predictions based off of this index alone to predict the MJO. But depending on the model, right now we have about a 12 to 36 day of predictive skill for the MJO. And this is from a paper from 2024. It only talks about conventional models. I don't think there's been a comparison with data-driven models. And then here is a figure from a different paper, but these results mostly still stand today. We're showing forecast lead day and the correlation score for predicting the MJO. And we're defining predicting the MJO by predicting the RMM. We're not asking about variable fields more than that. And then we can define like loss of skill score as going below 0.5. And if we take our Koopman mode and just predict by the eigenfrequency, just say we have something that has this approximate eigenfrequency and propagate it on, we get 15 days of predictive skill. So we're getting with kind of in the ballpark before we do any tricks, any actual ways to do predictive modeling here. So this could be a fairly helpful like index for these metrics and maybe for kind of predictive tasks. But so the spectral decomposition of these operators have provided us with like nice coherent form of feature extraction where we're getting these eigenfunctions and these Koopman modes that not only like vary coherently with our eigenfrequency, but also give us an eigenfrequency to like start having us interpret these modes. And this was pretty useful in the QBO case. It allowed us to like quantify this impact of nonlinear interactions between the QBO and the annual cycle. And it let us have a much smoother, nicer MJO index. And I think kind of to highlight for this group is I think there's a lot of potential for these Koopman-based indices to be used in model comparison and evaluation tasks. Like in the case of the QBO, it might be nicer to kind of train and evaluate on a very clear varying QBO index rather than a large wind field. And for the MJO, I think this could be true as well, depending on what you're trying to do. So I think there's really room here for this to be incorporated into those frameworks. And I think these have kind of some natural predictive abilities that they might be nice in future prediction tasks. But I have left kind of the relevant published papers here on the bottom, and I'm happy for more questions.